Okay. So here we are for another session of the NPTEL course on urban utilities planning, water supply, sanitation, and drainage. Um, this is the weekly live session. Um, the course is originally instructed by Professor Devapratim Pandit. He's an associate professor at the Department of Architecture and Regional Planning at IIT Kharagpur. I am a PMRF and a research scholar at the same department. I'm Monica S. So, before we start, to those of you who are educators or who have educators in their families, a very, very happy Teachers' Day. And I would also like to extend my gratitude for allowing me to interact with you and be a small part of your learning journey. It's just a matter of, I mean, it's not that I am a proper teacher. I also know only basics, and it's more like I took the course a year before you or a couple of years before you, and that's the only difference. So thank you for giving me this opportunity. As usual, we have two major means of interaction in these courses on NPTEL. First will be our weekly sessions every Monday, 7 p.m. to 8 p.m. Um, Before I proceed, pardon the background noise. There is a bit of celebration going on in our department for Teachers' Day. So I'm extremely sorry if there is any other interruption or anything happening. One second. So, yeah, during these sessions, you can raise your hand, unmute, and raise your query as and when we have a window after every question. So, questions can also be posted in the chat box. We also have a discussion forum for the course where questions can be raised and they will be addressed either there or in the next live session that we have. All right. So, a very brief recap of what happened in week 6 of the course, which was on water quality testing and treatment. So, the first two lectures were on water quality and testing. We basically covered concepts on potable water, impurities in water, physical and chemical quality of drinking water, bacteriological guidelines, recommended treatment for various sources, sampling procedures for testing. We also looked at physical analysis, chemical analysis, and biological tests in addressing or rather measuring water quality. The next three lectures focused on water treatment. We looked at treatment methods, sequence of treatment units, water treatment plants and their structure. We looked at individual components after that, such as screening, aeration, plain sedimentation, coagulation, flocculation, and clarification, as well as a third lecture on filtration, disinfection, and other treatment methods. We also saw a case study. So, in this session, we'll be basically looking at a few assignment questions from the previous round of the course corresponding to the same week. This week it's been mostly theoretical. We don't have any major numerical questions. So I would request you to participate more in the class so that we can have an actual like interactive session. Try to answer the questions. Try to recall as to what has been taught in class, and even if you don't know, the great thing about water supply and sanitation that I personally found very useful when I was learning was a lot of it actually probably depends on common sense. Like if you actually visualize it and keep a sequence to your mind, it's extremely easy to remember. So try to, even if, I mean, these interaction sessions, like nobody's grading you, so if you can just wonder ki, okay, what can the sequence be, or what can the answer be, or what can the process of treatment be, like where does it logically fall, then I think you would be able to answer both the ones here and in general pertaining to water supply, especially the treatment sequence part, right? So please make sure you send in your responses in the chat box so that it's easier for me to keep track also. Yeah, let's get into the session. So the first question for the day is, colloidal impurities in the water can be removed by A. Sedimentation, B. Filtration, C. Disinfection, and D. Coagulation. We have one answer.
It's decoagulation.
Right. We have one verbal answer. Is anybody else in the session? Okay. Right. So the answer, as we can see from the slides on colloidal impurities, is coagulation. You both of you are absolutely right. So coagulation basically depends on some sort of additional chemical being added, which is usually alum, uh, and that's our answers. The issue with colloidal impurities is twofold. One is their size, but even if their size is not, they're too small to be filtered out or anything. But even if the size is not the issue, it's about the charge that they carry. So even if you let them try to allow them to settle down, they will sort of be constantly in movement, somewhat similar to the Brownian motion that we learnt in school. So these particles will keep sort of repelling away from each other because they're all of the same charge. And that is where the issue with settling down comes from, right? So moving on to the next question. Actually, in this lecture for today, feel free to interrupt me anytime because most of it is theoretical. I don't think we should have a problem with interruptions. Right. Excuse me. So, according to CPHEO, what should be the acceptable pH of the drinking water? And we have four options: 6.5 to 7.5, 6 to 8, 7 to 8.5, and 7.5 to 9.
C 7 to 8.5.
Okay, okay. Anybody else? You are absolutely right, Miss Supriya. The answer is 7 to 8.5. The thing is, as Sir had also mentioned, one thing to be noted here is, I mean, there is a gray area between the acceptable and the rejection range, right? So, 7 to 8.5 is the acceptable range. However, less than 6.5 or more than 9.2 is the rejection range. What happens is there is a gap between 6.5 and 7. So, these are the tolerable limits. If you remember how Sir had explained that this gaps is sort of, it's not okay, but all right, I mean, let's tolerate this much of a deviation. However, I think almost everywhere, except in cases where water is uh, not treated to any extent and it's sort of lying in the border, and any kind of treatment is either not possible because of economic reasons, or it's so, the gap, the differential is so minute that it doesn't make sense to add another component to make it, within the acceptable range. That is the only time when you don't go for treatment. Otherwise, you usually try to maintain it between 7 to 8.5, right? So the
I have
answer
one
is,
question.
yeah, yes, ma'am.
Alkaline water has different pH, or is it the same drinking water?
So water in general is slightly alkaline. So 7 is neutral, right?
Okay.
You see that drinking water is usually 7 to 8.5. So
Right.
alkaline water is probably slightly higher, but within this range. We don't go for beyond 8.5. I mean, say the maximum is 9.2. So usually alkaline water, what they refer to as alkaline water, is also within this range.
But in assignment question, the range is given 7 to 10, 7 to 18, 7 to 14, 7 to 15. So it was bit confusing for me.
The
That's why.
current assignment.
Yeah, current assignment this week only.
One second.
Question number 15 it is.
I'm opening the assignment.
Assignment 6, week 6.
They're asking about the complete range of alkaline water, like any water that is alkaline. So there is alkalinity. Is it alkaline or not? Yes, 7 to 14 is alkaline, right? But what is the acceptable range within that alkalinity is 7 to 8.5. I thought you meant, so
Oh,
generally there are people in marketing of water who claim that alkaline water is good for you and package it as alkaline water, right? I thought you meant we were talking about that. But in general, when you talk about the range of alkalinity, it's 7 to 14. That's the full range.
okay, I got it. The acceptable value and the range.
Yeah, yeah. Full range is 7 to 14.
Yeah, okay. Thank you.
Yeah. So next question. Which physical property of water is measured by nephelometer? A. Turbidity, B. pH value, C. Total solids, and D. Taste. Any answers?
I guess it's turbidity.
Okay. Okay. We have one answer, turbidity. Anybody else in the chat box or? Okay, the answer is turbidity impact. So if you remember from the slides, we spoke about how nephelometers are used for measuring turbidity. So it basically uses the intensity of reflected light to measure the degree of turbidity. So, but please keep in mind that nephelometers are actually available for both air and water. Essentially, they nephelometry is the term that is to refer to detection of light energy scattered or reflected towards a detector that is not in the direct path of light transmitted. So whenever you transmit light, so the essential measurement logic is you measure reflected light, right? Like whatever is scattered by the constituent particles. So that is how you essentially look at nephelometry. And nephelometry actually comes from the word nephil, which the Greek word nephil, which means cloud, right? Just some extra trivia. So any kind of measurement that actually includes you passing light through the medium that you're checking, and where you are actually measuring the scattering, the amount of scattering. So the scattering will depend on the concentration of, like, the number of particles which are there, right? Like the more the number of particles within the medium, the more is going to be the scattering, right? That's one thing. The other thing is, if nephelometers actually are designed to sort of take into consideration differences between the types of particles. For example, say you have particles that are predominantly darker in color, the amount of scattering will be slightly different from how it will be if it is a lighter colored particle, or from the size, or from various other physical properties of the particle itself. So nephelometers actually have a provision where you can enter what type of particle you actually have in the suspension, right? But there is also a generic option where you can sort of measure turbidity even without knowing what the cause of turbidity is or what kind of suspension it is, right? So the answer is thus A, turbidity. Moving on to the next question. Match the following and mark the option for the correct match, right? So we have four options to the left: photometer, starch iodide test, electrometer method, and diometer. And towards the right, we have pH, color, oxygen, and chlorine. So, can I get an answer for just photometer? What do you think photometer is actually used to test for?
Color.
Okay. Color, yes. We have two answers, both right, absolutely right. We use it to test for color. And let's go for the slide. So photometer is essentially, as we can see from the slides, so we it actually measures in platinum cobalt units, if you remember, which is, so whenever we are setting the standard unit for these measurement devices, even turbidity for that matter, the standard unit is measured like one PCU or one NTU is measured based on some form of basic component that the international standard has set, basically. So in this case, platinum cobalt happens to be the standard used for measurement. Therefore, it's called platinum cobalt units, right? So the second part is use of starch iodide test for chlorine. So this slide is actually quite uninformative in the sense that we don't actually know how a starch iodide test works. So let's take a look at what the test actually is. So whenever you have a sample to be tested, and what are you testing for? You're testing for the presence of chlorine, right? So you add a combination of some form of starch and potassium iodide into the into water that you want to test for the presence of chlorine, right? So if there is chlorine, the water turns blue. If it's there is no chlorine, the water doesn't turn blue. So what is the mechanism behind this? Essentially, when you add potassium iodide to water, if there is chlorine present, if you remember again from school science, there is something called a reactivity series, right? So say there are two components, A and B, and if A is higher in the reactivity series than B, then if you introduce a compound of B into A, what will happen is it will be replaced, right? So in this case, let me take my pen. So chlorine is actually higher in the reactivity series than iodide. Basically, the capability of it to react with anything is higher than iodide, right? So when as soon as you add this potassium iodide into the solution, if there is any chlorine present, what will happen is this chlorine will replace this iodide, right? So we'll end up getting potassium chloride salt, and we'll have ions in the water, right? So, and it so happens that whenever you have iodine ions and there is starch present, this combination gives you that blue color. So this blue color is actually arising from the emergence of iodide component. So I'm sorry, here it is chloride and iodide actually, because they're ions, right? So Cl minus and I minus. So if there is no chloride present, chlorine ions present, or free chlorine present, then there will be no iodine or iodide for reacting with the starch, and therefore there will be no blue coloration. So that's the basic logic behind this potassium iodide starch test. In fact, this test is actually employed in solutions or liquids that are not water, like including milk and all, to test for the presence of chlorine. In case of milk, it's actually an adulterant, right? In case of water, it's all right. So when you detect the presence of chlorine, what you do is the quantity of chlorine is then further determined based on the number of ml of thiosulfate that is required to remove the blue color. So when you titrate, you keep adding some thiosulfate to the solution till the point that the solution stops being blue, and then you multiply it with the value 0.355, right? So that is the quantity of chlorine that's present in the water sample or solution in milligram per liter, right? So that's a basic introduction. pH is actually measured with electrometric method, right? Where you dip electrodes into the water and connect it to a dry cell, and the meter will give you the pH value. And dissolved oxygen is obviously measured through a DO meter. So here As you said, photometer is for color. Starch iodide test is to test the presence of chlorine, like we saw. Electrometric method for pH, and dissolved oxygen meter for oxygen. Right. So the answer happens to be B. Any questions till now?
No, go ahead.
Okay, all right. So next question. The presence of nitrogen in water mainly indicates presence of organic matter and bacteria and dissolved gases, suspended impurities and ammonia, and organic and inorganic material.
It's C, suspended impurities and ammonia.
Okay. Okay. Any other answers? Okay. Let's look at what the presentation talks about. So, nitrogen actually indicates the presence of organic matter and bacteria, which is also by extension, I mean, living organic matter, right? So that's our answer for this question. In fact, by figuring out what kind of nitrogen component is present in the water, we can sort of uh, determine what kind of what stage of composition is present in the water, right? Or how much of oxidation has happened to this organic matter. So we can have free ammonia, which indicates first stage of decomposition or contamination having happened very recently. Then we have nitrites, where which is allowed, right? Like, so a very small amount of it is allowed. Nitrates are absolutely not supposed to be present in water. So where you it indicates part decomposition, which means organic matter is sort of partially oxidized. Then we have nitrates, where it is fully decomposed or oxidized, like the organic matter is completely oxidized. Or we have organic nitrogen, which is before the beginning of decomposition. Right? So these are the things that we can understand from the presence of nitrogen and the type of nitrogen that's present in our sample of water. So the answer is actually B. It indicates the presence of bacteria and dissolved gases. Right?
Can you please go back to the slide where you
Yeah,
were
yeah.
explaining? Actually, I got confused. You said organic matter and bacteria, and then it's dissolved gases and bacteria.
And sorry.
The correct option you said bacteria and dissolved gases, right?
Oh my god. I think one second.
Is it organic matter and bacteria only, right?
One second. It is organic matter and bacteria. My
Okay.
bad.
Oh, actually, I thought I missed something.
No, no. You're absolutely right. I think I just went on auto mode. It is
No problem.
organic matter and bacteria. After
Okay,
so
no
much
problem.
explanation, I can't believe I made that mistake. Thank you for pointing it out. It is organic
No,
matter and bacteria.
it's no problem.
Thank you. So, moving on to the next question. Match the following and mark the appropriate option for the correct match. Right? So, we have four types of impurities that we're looking at and four types of treatment methods. So, for silt, which treatment method do we use? Any answers? Or if you know any of the four, you can actually go ahead and tell me. Scum, dissolved gases, or microorganisms. Any one of the four. Okay, so we have one answer in chat box. I assume that's for silt, right? Somebody has come up with sedimentation, right? Okay, so okay, final answers are coming up. So the answer that's been suggested is D.
It's D only.
right? So silt sedimentation. Right. Let's see the slides. So this slide essentially summarizes all the treatment methods that we have. So silt is suspended impurity at the end of the day, so we require plain sedimentation for its settlement. For scum, we require clarification. So essentially, clarifier is the one that is present in the sedimentation tank, the settling tank, right? So in that settling tank, we have this scraper on top of the water body. So if you have this, sorry, this should be longer actually. If this is the tank, settling tank, we have something like this on top actually, sort of a truss kind of system where it scrapes all the scum that is floating on top, right? So that's how the clarification process removes scum. And we have dissolved gases, taste and color are removed through aeration. Basically they end up replacing the gases inside. And we have microorganisms and colloidal matter being removed through filtration. So sometimes we also have, it's not just a normal filter, some of the filters can be biofilters as well, where we employ some form of medium that can actually enhance the filtration of microorganisms present, right? So the answer is D, as all of you have pointed out, right? Moving on to the next question. The correct sequence of treatment units for groundwater with excessive iron, CO2, and odor is sedimentation, rapid mixing, and chlorination, or B. Sedimentation, slow sand filtration, chlorination, and demineralization. C. Aeration, rapid mixing, flocculation, sedimentation, rapid sand filtration, and chlorination. And D. Rapid mixing, sedimentation, and softening. Do we have any answers?
I guess it is C. It is because CO2 is present, so aeration is required.
Okay, okay. And even Mr. Rahul is suggesting C. So the answer is C actually. So if you look at the slide, this process is actually been highlighted in the slide directly itself. So we employ aeration to remove carbon dioxide as well as odor to a certain extent. And to be honest, aeration also will end up precipitating a lot of iron, if you remember, right? Which needs to be filtered out later or allowed for sedimentation. But because of aeration, some sorry, I don't think I included the sites. Some of the components like iron also start sort of materializing in water. So that's the major process that's differentiating. All the others are sort of components addressing the groundwater part, what is usually required for groundwater. So the answer is aeration. Then we do rapid mixing, flocculation. Rapid mixing and flocculation will remove any of the colloidal or suspended, very small suspended particles. Sedimentation will allow the settlement of these particles. Rapid sand filtration will remove any kind of it will allow disinfection essentially to a certain extent, as well as remove some, do some more filtration. Then we have chlorination for disinfection primarily, right? So that's all. This is the key here, aeration, right? Next question. Identify the water treatment units as shown in the figure. So can somebody tell me what A is? So for A, we have two options, right? Like screens or plain sedimentation tank. Right. We have Mr. Ashwin telling us that it's sedimentation tank, and Mr. Rahul telling us it's screens. Okay.
It's a screen. B will be sedimentation tank.
So actually, this is our source of water, right? We're taking water from the river, and we will be taking water in through a pump, right? Which means this is our intake point, and this is there is some sort of pump here, right? If you remember, screens are employed before pumping to remove all kinds of large, very large items. It's not just like so. There is it's two pronged, right? One is the screen will help in the treatment, which also removes, also involves removing big objects, but also to ensure that the pump is not damaged by the presence of these large things. If you notice any of our rivers, we have what not floating there. So the screen will actually be employed somewhere here, right? Because this is the pump. Screen is actually sort of pre-treatment, if you if I'm allowed to use that term. So the actual answer is A. Plain sedimentation tanks is the first component in the actual water treatment plant. The screen will be placed before the intake point or the pumping point, right? So, which means the first one is plain sedimentation tank and not screen, right? The second one, B, what do you think it is? Do you have answers? We have flash mixer from one person. Any other answers?
Class mixer.
Yes, yes, absolutely. So it is flash mixer where we'll be adding the chemical that will enable further flocculation, right? So that's the first step. Flash mixer is essentially one fan that will rapidly mix the agent, flocculating agent into the water. So that happens in this flash mixer. So B is flash mixer, which means we have already sort of narrowed down to the option D, right? But let's look at the others also. C will be then flocculating basin, if you remember. So this whole component is the coagulation flocculation part along with this part where sedimentation happens, right? So this entire thing is the coagulation, flocculation, sedimentation, that component. So this part you have mixing of the coagulant and you have the flocculating basin. D. So usually in most diagrams, the next component, especially the one with this triangular scraper at the bottom, is a settling basin. Why? Because we have these scrapers to sort of remove the sludge that gets accumulated in the bottom. So if you again, the scraping sort of happens here, right? I'm sorry about the drawing. The scraper will be somewhat here. It won't be this big, very out of scale, to remove all the floating components, right? So then we have E, which is rapid gravity filter. So for further filtration, water goes in, and we have F is chlorinator, which adds chlorine before being supplied to the city. But can someone tell me what these two tanks are?
The top one is used to backwash,
Yes,
and
yes,
the middle one is
right, right, right.
filtered water. You can for
Absolutely. So
chlorination.
we essentially have it as backwash structure, right? So if you look at this image, these are the You can see that this is the sedimentation tank, flash mixer, flocculating basin. So this is the place where all the chemicals are stored, therefore being helping us identify the flash mixer part. Settling basin, rapid gravity filter. The clear water tank is essentially just an intermittent storage. It could also help in the further functioning of this wash water tank. And then you have the chlorine, right? So the answer is D. Yes, as Mr. Rahul has also put in the chat box, right? Any questions till now?
No, please go ahead.
Thank you, thank you. So next question: which factors influence the sedimentation of particles during the treatment of water? Temperature of water, viscosity of water, pH of water, and density of water. Any answers? Okay, we have one answer B. This is all of the above. Hmm. Any other answers?
Yeah, I guess so. It's all.
Okay. So actually, we are particularly looking at the process of sedimentation, right? Which means we'll be primarily looking at aspects which are pertaining to the physical uh, or influencing the physical settling down of particles, right? So, if from the slides that were part of the main lectures, we can see size, shape, density, viscosity is there, temperature is there, surface overflow rate, velocity of flow, inlet and outlet arrangement, detention period, and effective depth of settling zone. So, since pH is more towards the chemical property of water, it doesn't actually directly influence this particular aspect, the sedimentation aspect of treatment of water. So the answer is actually A, B, and D. Okay, so that's where so temperature sort of determines colder the water, lesser is the movement of particles, right? Hotter the water, more is the movement of particles, which means sedimentation will be more difficult relatively. Viscosity is basically the essentially the density of water and viscosity of water. Both of them will determine how much rather viscosity will determine how much the water is moving around, right? If it's a thicker liquid, more viscous liquid, the movement of water will be lesser, which means rather it has more components, so there is more settling. Also there is movement, lesser movement of water, right? Any liquid with more viscosity will move with more difficulty. The density of water again determines sedimentation, because one, the amount of components that is going to settle down has to pass through the entire body of water. So if the water is denser, it's going to impede sedimentation again, right? But pH doesn't really have a direct effect on sedimentation. Moving on to the next question. Identify the correct sequence of steps of chemical sedimentation. So feeding, mixing, clarification, and flocculation. Feeding, mixing, flocculation, clarification. Feeding, clarification, mixing, and flocculation. Feeding, flocculation, mixing, and clarification. One answer B,
Option B.
and we have one D.
B for
B.
bombing.
Okay. So from the slides we can see that it's actually feeding, mixing, flocculation, and clarification. So the answer is in fact B, right? So this is a very direct theoretical question from the content that was presented in the slides, right? Next question. A typical length to width ratio of rectangular sedimentation tank design is 3 is to 1 to 5 is to 1, 4 is to 1 to 6 is to 1, 2 is to 1 to 6 is to 1, or 4 is to 1 to 5 is to 1. Any answers?
It's a 3 is to 1 and 5 is to 1.
Uh, A. Your voice code.
Yeah. Yes.
Any other answers in the chat box? Okay. Yeah, you guys are absolutely right. So that's the answer. So the reason why we have such a where is my 3 is to 1 to 5 is to 1. So the linear nature of the sedimentation tank will sort of ensure that there are no eddies or currents. So because a broader one will sort of enable movement or circular movement, especially within the uh, entire stretch. So if it's linear, the probability of these eddies or currents forming is much lesser, right? So we also try to break down slightly broader tanks into different components, if you can see, so that each linear stretch is sort of isolated, and movement in anything, any one will not affect the other, right? Like so, the settling is also easier. So our answer is 3 is to 1, 5 is to 1. All right, next question. Which statement is incorrect regarding sand filters? A. Depth of the sand bed should be between 16 to 90 meters. Uh, it's actually centimeters, right? Centimeters. Not wrong. Technically, it's okay. Let's take that it's 60 to 90 meters. Sand media should be supported with a gravel bed. Effective size of sand particles in the sand bed in a slow sand filter is less than that of a rapid gravity filter. And rapid gravity filters do not require backwashing. So, answers, we have 1D. You're right, Mr. Rahul. So, first of all, this is a mm, typo. Sorry about this. It's centimeters, otherwise, both A and D are wrong. So, we can see that the depth of the sandbed in from the slide, we can see that it has to be 60 to 90 centimeters, and it's usually supported on gravel bed. So what happens is it's sort of allows the water to pass through. It's like a mesh essentially with additional um, gravel so that the sand doesn't go through the mesh, and it so happens that gravel also provides a certain level of filtration. One second. Yeah. So and slow sand filters versus rapid gravity filters. Gravity filters do have larger size. Why? Because it so that it allows the movement of water more freely. Otherwise, you will probably end up putting the system under a lot of pressure, and water will not come through if it's a very small uh, size, right? So also, let me explain this uniformity coefficient. So, essentially, you have two values that you need to calculate. Whenever you have a filter medium, you have a bucket of sand that you're going to use for filter. First of all, you run this medium through a sieve. Okay, this is sieve number one. Sieve number one, you decide the size such that 60% of this will pass through, right? Which means 60% belongs to size of the sieve or lesser. Okay, and then you take the entire thing again, you mix it, you pass it through a second sieve. This time 90% of the particles, the 90% of the grains, the sand should pass through, right? This uniformity coefficient is a ratio of S1 and S2. That's the uniformity coefficient, right? Just to clarify on that point. That being said, rapid gravity filter, the option says that it does not require backwashing. However, it does. So why? Rapid gravity filter essentially works on under a lot of pressure, right? So when you are putting this much pressure, so here you can see these things. So what happens is a lot of these sedimentation happens very quickly, and it sort of gets deposited majorly on the top, but also in between these particles. So what we do is we sort of send in water through the other direction. After stopping operation, of course, we stop the operation and then we send in. So it's like a reverse cleaning. We turn the system and then send water through the other direction, so that all the coagulants that have sort of blocked the passage of water can be removed. Right. This is the case in pressure filter also. Actually, they also employ backwashing. Right. So the answer is D. Yeah. Sorry about the type. Right. Okay. Next question. In rural areas, disinfection of water in wells and ponds is performed by adding A. Iodine, B. Lime, C. Potassium permanganate, and D. Chlorine.
Chlorine.
And we have one answer in the chat box. Two answers.
Yeah, yes,
I
it
see.
can be LM like potassium permanganate also.
Okay, so you have said chlorine, ma'am, and we have three options in the chat box saying that it's potassium permanganate. The answer is actually potassium permanganate, right? So if you remember the slides content, it's actually used in villages for duck water. So even I didn't know this. I had to do a bit of digging to figure out why is this the case. I mean, any day chlorine is a better disinfectant than potassium permanganate, and not that chlorine is not, like, chlorine is also not too expensive, right? It's one of the cheapest that we have. You just put bleaching powder and your disinfection is done. However, there are a couple of possible reasons why I think, like, or rather from online sources. First of all, one thing to note is that potassium permanganate is actually not a disinfecting agent. It's an oxidizing agent, right? However, it can sufficiently manage disinfecting against one particular bacteria, that is cholera bacteria, right? So there is a possibility that in rural areas, because of uh, the mixing of organic content, especially fecal matter. If you remember, sir also pointed out in the slides that the mixing of fecal matter is something that you cannot really control much in rural areas because of two major reasons. One is naturally animals and the number of cattle and all is higher, like generally in villages. But apart from that, one other reason is that open defecation is a very normal or a very prevalent thing, right? Therefore, targeting cholera is something that makes sense. In fact, KMNO4 actually addresses KMNO4 as in potassium permanganate actually addresses both cholera and gastroenteritis, right? These two are sort of uh, issues of the gastrointestinal system, and it makes sense to target this. However, if this is the only thing, even chlorine can do this, right? The additional benefits of using potassium permanganate are: one, it removes the odor and taste because it's a very strong oxidizing agent. It oxidizes any of the organic material that is present in water in the well, and hydrogen sulfide. Again, hydrogen sulfide is an issue whenever fecal matter or any kind of deep organic matter is going to be mixed in water. So it sort of removes the odor and taste coming from the presence of these. It is not as good as removing the presence of these, yes, correct. But given that in rural areas people don't usually sort of put in place advanced treatment units, it basically makes water more palatable, right? By removing obvious indications of pollution from water. And then other aspect is it actually removes or rather prevents algal growth. So in wells, just the addition of the MnO4 can help you address more than one component. On a more chemical level, it also creates iron and manganese compounds out of dissolved iron and manganese. So what happens is iron and manganese will start precipitating in the water. However, even if it precipitates, you have to further filter it. Like, it's not that it automatically disappears, right? But nonetheless, at least from the dissolved state, you can bring it to precipitation or some kind of solid that you can remove from the water. So because of these sort of this sort of comprehensive use that potassium permanganate gives, it's actually employed in uh, villages, like rural areas, for disinfection in, especially in, usually the source of water is well. That being said, two components have 2 points to note. In general, it's advised that potassium permanganate should not be used as a disinfecting agent. Like, the question actually talks about, is it actually used or not, which it is, but it's not really a good thing to do, right? And any day, chlorine is a better agent. Right? So, moving on to the next question. Which treatment technique is recommended for the treatment of salt water? Again, direct question from the lectures. A. Distillation. B. Fluoridation. C. Water softening. And D. Oxidation. We have answers in the chat box. A. Distillation. Any answer? Any other answers?
Distillation only.
Yeah. All of you are absolutely right. It is, in fact, considered the best method for treating salt water. Right? So that's the presentation for the day. Are there any doubts in general or any other inputs? Anything?
No, thank you.
All right, all right. If you have any other feedback or anything else that you would like me to address, please mention here or in the discussion forum. I'll try to address it. Right? Hope you. It's almost 8, so I think we are close. We can close for the day. Have a good day, all of you. Thank you for joining the session.
Thank you.